Thank you very much for inviting me here to talk about something that is, as Antonetta said, it's 30 years. Being a metallurgist, you don't just, as you correctly say, just learn in the backyard. It's a whole lifetime. Permit me just, and I don't believe many of you know Outotec. Just give you a short introduction with one sheet, and then just dovetail a bit to what Antonetta has said and come from a technology supplier point of view. We build plants, we design plants, and I'd like to intimate this with you. As you said, that is our turnover, our knowledge base, our patents. It's know-how, deep know-how, to build plants, to make them work. The word economic came up a few times. That's our business, and it's related mainly to the building and designing of plants to make metals. And ultimately, it has to be profitable. As it was also mentioned by the Sims, we're also on that list, 12th, which is interesting. It's an interesting change that the top company is Umicore on that list. We're on the 12th on that list. We are technology supplier in metals, being sustainable, and you're doing your recycling business. So it's very interesting to see that dynamic happening. And that's the exciting of this group of people coming together, actually speaking about this. I also highlighted in red there, we have knowledge in-house to process and recover a fair bit of the product table. Now that's not just recovering it, it's making it work in a technological environment, extracting metals, not only from primary resources, but from recyclates, e-waste, scrap, residues, slimes, etc. And also recovering energy from that, and therefore bringing the energy and the metal side together, because you can augment the one with the other to make your process more efficient. I don't think there's a place, at least in sort of the Western, and I am a professor in China as well. There are 300 students in the lecture. In Delft, there may be 10. So it's another dimension. But if you would look at our company as metallurgists, we've probably got 100 parametallurgists, 100 highly trained, PhD level, which would speak about this, hydrometallurgists, mineral processors. And that's really the strength of that. And quite uniquely, we've supplied over 130 smelters. And I'll just intimate with you a bit later slightly more detail on that. That covers flash smelting for copper, which is the copper-making technology. Caldo, TSL. Now that means top submerged lance. I will show you a bit of a video, just as I'm seemingly the only metallurgist or pyrometallurgist. Not even my two students, ex-students, put up their hands when they were asked of metallurgy. But I'll try to just show to you what that technology looks like, because ultimately, as a pyrometallurgist or metallurgist, we have to take the junk and we have to make metals. And that's sometimes not so easy, and I'll explain that. Oh, just before how do I return one? The red button. Also very interestingly, and I'll show that to you in a graph in the next one, 50% of world copper is produced in Outotec technology globally. If you look at the PGMs, platinum group metals, more than 30% goes to Outotec technology in South Africa, in Rustenburg. All the converting done at Anglo Platinum goes through our converter. And also the tin production is significant. So the metals we produce with our technologies is a significant percentage globally that is used presently. Then just some extra information. We produce sulfuric acid plants. We've built the largest globally. Minerals processing. So we have very, very deep knowledge about minerals processing. We're not in the scrap sorting and scrap separation business. Our competitors, for instance, Metso are, but we have very, very deep know-how about physical separation and the issues involved there. Iron making, ferroalloys, light metals roasting. I won't go into that detail. And just while you were probably looking, you can see those photos. The largest pelletizing plant in Brazil comes from Outotec. Now just with this, I'd just like to give you a bit of a feel for what is happening. When we speak about recycling, about metals, there's always this difficult bit at the back, and I'm not saying by any chance that physical separation is less difficult. That whole cycle, bringing it together as Antoinette has tried to do, is one of the key issues I'd like to discuss with you. But here you see some of the pictures, especially the bottom right one. That's the level of the BAT used in China, and it comes from our company. Just to wake up, a bit of a wake-up call, just looking at that graph, say about 20 million tons of copper are produced per annum. And the graphs show simply the growth or decrease of copper production in various places of the globe, but also the fraction of technology used, in this case for copper production from primary. But if you look specifically at China, what's happened in the last couple of years, it's quite significant. And interestingly enough, 70% of that copper is produced through Outotec technology at the BAT level. So it's not a dirty dump anymore. They're doing better than we are. The other very important message, take home, if you want to recycle, you need some base metal know-how. If you've lost it, it's gone. If you don't know how to separate metals from each other, you can't recycle them back into whatever product you'd like to make. And fortunately, unfortunately, copper is an extremely important metal to close the e-waste cycle. But not only copper, the lead, and the related metals, perhaps zinc, together create a block that are required to capture those metals and bring them back. If you lose that by policy, you can speak about resource efficiency at EU level. It won't work. Your metals will be recovered at some other place where they know how to do it. Ultimately, speaking as a metallurgist, we create metals at London Metal Exchange prices, and that has to be profitable for us. And we try to minimize the waste as far as we can. That's our business. That's been the business we've been doing 30 years. There's nothing new to it. So all these nice words of resource efficiency, you can speak them, but you have to walk the talk. You have to make them work. You have to go from your input to your output and minimize the waste, maximize the profit. While I was speaking, you've had a chance to look at that. Take note. Things are happening, and they're happening pretty fast. Look at that graph. And as I said, we are very, very much actively involved there. You've seen this figure in another version earlier today. But let me just explain it from my perspective, how this came to being. And there was also one of the questions that came up a bit earlier. 30 years ago, I did my master thesis in South Africa. And we were looking at minerals, and we were trying to control and optimize flotation plants. That is the separation plant to go from the mineral to the concentrate. Very much like going from end-of-life product to scrap concentrate. At that time, the models were poor. The data acquisition was poor. The measurement was poor. But at least there was one thing. People came together and they laid down some rules, how to collect data, how to simulate, how to model, to be able to do what we do today. We take the simulator that you saw earlier today, we design plants on that. We control plants with that automatically, for process control. In other words, in that period of 30 years, we've evolved significantly. And that's the challenge also of the recycling industry, metallurgy industry. It's virtually a mirror of each other. If we start connecting the rock to metal, end of life to metal through the recycling chain, we can talk business on that very fundamental basis. This figure tries to show it. We do it. We design plants this way. And you've seen the significant plants. The biggest copper plants, for instance, to remain with copper, are in China. They've got the knowledge. They've got 300 students sitting and doing metallurgy. They're going to put ears on us as well if we don't take care of that whole chain. We have to fight for the whole system. Now, as you can see, that geological mineral takes a significant plant to actually go from the mineral to all the recovery of all the elements. It's a significant capex investment to do that. Now we know where, and when we design a plant, we know what goes in and what goes out. We have to do that for environmental reasons, but also primarily because of the cost reasons, the profit. We want to make metal. We want to make intermediate products or high-end critical element products that are associated with that mineral and produce them and ultimately going into products. But the step to the, and Antoinette, and I'm not going to repeat what she's done, the minerals are even more complex. So you have to be pretty, not just say we are the greatest in this industry and we're the greatest in that. You have to marry your concentrate with a plant. Because often I feel, as a metallurgist, we were the dump heap of scrap coming in, and we have to deal with it. We have to package the metals, the arsenics and the cadmiums and whatever comes in. We have to put it in our off-gas or into our slag, into our spice. We take and carry the can. And that's difficult, so you have to harmonize these aspects to optimize and at least look at that bigger plant. So, just something more specific to Outotec. Some plants, just to show you it's real. The top left-hand is a Dawa plant. Usually we hear of Umicore. We hear of Aurubis, all good friends, because I know of many people there. But also Caldo. Caldo is also Outotec. It is Polydon. But in the end, whichever supplier or every company we are, we have a very, very important role in this playing field of closing the loop. Closing, I always say in inverted commas, because there are so many beautiful stories, and then I always ask, have you heard of the second law of thermodynamics which permits you not to do that? And then people look at you with glazed eyes and say, what the hell are you talking about? It's just not possible to close the loop, because you will always have, by nature's law, losses. But at least the physical recycles, the metallurgists, are trying to optimize that as far as that is possible. And that is our job, and that is our expertise. So here's some plants. I've been very much involved, for instance, in the Dawa plant. I've sat there. I've optimized it. I know of X metals coming in, and X is a pretty large list, where they go and what they do with it. That knowledge you don't find in textbooks. But speaking together in a language which everybody can understand, you can get a good feel what is positive and what is negative. And at least we try to do it. You can't recover everything, but at least you, within the economic environment of each plant has its own business plan and whatever they want to do, and recover the metals accordingly. Anyhow, these are all Outotec plants, which, by the way, you could have a look at now. Bit of Japanese. I'm sure you've seen the Umicore plant many times, so I'm just showing you another one. This is the Dawa plant. Doing the same thing. Metals come in, mixtures come in, and they know where to put them. It's not just one reactor. It's a whole host of joint technologies that actually make it happen to recover all the metals that come into that. So obviously, within the boundaries of what you can do, with what your technology can do, you can extract them and produce pure metals again and recycle them back into the chain. But here's just another example of a plant situated in Kosaka in the town and running at the highest level of environmental compliance. You've seen this, and I just had to show it again. Now, I hope I didn't understand what you said, that it could be all too academic to be pointed. This is what we do to analyze systems. When we go to plants and audit plants, we take these tools and we optimize it for our clients. We've built the plants, but we also help them. These are the tools to optimize resource efficiency. It happens. We do it. We do it for a business. I won't go into this either, but at this point, and I may make you aware of a report we did through United Nations on metal recycling. Two of the co-authors are sitting there. It's one from Umicore, Antoinette as well. So we produced this document to disseminate for free knowledge of that cycle, the knowledge that you require to improve resource efficiency as far as that is possible within the constraints of that system. Have a look. You can download it by just Googling and metal recycling UNEP. You'll find it. 3 years ago, top submerged lance technology was invented in Australia. A very inventive time, I think, in Australia, and by John Floyd. There are two variants of this technology. One is at Umicore, at Aurubis. The other one is, which the inventor actually carried on in his company, which I joined in 2005 in Australia. That has built plants in Dawa, in Korea, also 2 plants in South Korea on these, based on this technology. I'd just like to use this then to be bipartisan, and just to show you what goes on in a reactor for 4 minutes, just to keep, I think most of you have probably not seen the inside of a reactor, just to give you a feel what we as processors of materials, whichever they may be, have to deal with, and to be inventive and to understand economically how to do that. The word economic came through very few times. That's what we do. If it doesn't work, you kill it. And obviously that plays around, and within the constraints and the dynamics of changing feed materials, you try to maximize the recovery. And that's our job as metallurgists in the whole material cycle. Okay. TSL is a pot, basically. You can call it a cooking pot. Just get a feel of the scale. You see a person at the bottom left now moving around. Just to give you a bit of a scale of this type of pot, at which you are processing a feed by manipulating the chemistry. And this is how deep I will go into thermodynamics today, to manipulate that to recover those materials. In this case, the lance, which is what the word comes from, top submerged lance, it's similar with Umicore, with Aurubis, with Dawa, with other plants as well. To manipulate that with that lance that is injecting fuel, certain gases, to manipulate what happens in the molten bath. And this all happens at temperatures around 1300, even higher. 1350 are processes that we use. Not only can we use primary energy sources, we can also use the recyclates. That's why the balance of an e-waste with its scrap plastic, with its valuable metal content, if you balance those right, you can use them, you lower the footprint of your process. So you don't have to shred to infinity. By cleverly playing with that whole field from the recycler to the metallurgist, you can achieve a lot. In this case, the whole trick, and this was the real invention, that if you stick a steel pipe into a molten pool of slag is this molten oxide, you may think, well, it will all melt away. But the technology really, by freezing slag, which is this molten rock material, onto it, you protect it. And you have this splashing environment where very intensely you can process a variety of feeds. So we've used this technology not only to do scrap recycling, e-waste recycling, but as I've said, we've made copper in it, nickel, PGMs, tin, lead, zinc fuming, indium fuming. People are speaking about indium. We fume it. It's been done 10 years already. Nothing new. So the EU projects going on, which are really overhauled and 10 years old. So that's what's happening inside there. And obviously, having this technology, you have to maintain this material which is at high temperature within that vessel. That's the trick. The diameter is about 5 meters in the inner side. And you try to at least make sure that that reactor doesn't blow apart. So as you can see, a highly dynamic, flexible operation, which, as I've said, permits you to go anywhere you like. For instance, in Namibia, we've designed a plant for lead. It's now making copper. That's the true innovation. The true mark of metallurgy is actually to play around in that field to make it work. So that harmony between recycler and metallurgist is of extreme importance. So just to summarize this street, don't go into the detail. With the same reactor, we've made lead, as I said, zinc, and all those metals, but we've also made iron. In the same pot, with the same reactor, but with a deep knowledge, you can do that. And that's just showing that. Now, I have to show two types of graphs, just to highlight what we have to deal with. And this is a very simple one. People speak very easily, we have to remove aluminium. I'm just going to show you quickly what the effect of aluminium does to a smelter. Now, if you look at the axis, if you have a molten material, it's like lava at 1300 degrees. If you add aluminium, the freeze point changes. It solidifies. So if you look at the y-axis, it's the percent liquid, the amount of alumina, and the temperature. The top orange plane tells you when it melts. Just have a quick look what happens if I change the conditions. And I can play around with it, but that's what we have to deal with. Okay? Do you want to see it again? I have to show this. We speak about recycling, but we stop. Aluminium is bad. No, it's not always bad. We can deal with it. But we can only deal with it to a certain point. So you can have these beautiful design for recycling rules, but you have to understand that. So you have to play around with that. So to link the two is of extreme importance. You can get away with it, but you'll use your aluminium, but you'll gain the other metals that are of importance. And within boundaries, you can optimize it. So can you put that in a design for recycling rule? No, you can only simulate that, and we can do that. It takes 5 minutes to do. And then the EU spends 1 million, 2 million of taxpayer money on research, which we can already do. That's very critical as well, but it makes me angry to see that happening. Then just as a final overview sheet, this sheet just shows to you what happens with elements. Depending on how you run that furnace, the metallurgy, that depth, you can get different results. You can play around with it. Ultimately, the company wants to make profit. It wants to recover the metals into the right fraction. But each mixture is different. Each mixture creates other materials that can either volatilize, or they can go into the metal, or they go to the slag, or they go wherever. I'm just going to zoom through a few sheets just to give you an idea. That is the trick of metallurgy. That's why people have to talk, to be able to understand this in depth. Okay, so I come to my last sheet. And I promised I would not give you a metallurgy lesson this late in the afternoon. And I'd like to end off, and I had a question just over tea time. Where can I learn this metallurgy? Unfortunately, there are less and less good metallurgists around in the EU. And we have to make sure that we maintain that. And there are some initiatives that are actually trying to do that. And then I don't mean textbook metallurgy, real metallurgy, to know and understand where things go. Just as you had said, understanding how you recycle, where those fractions are going. That's the depth. And you just don't find it anyway. You have to talk to the right people. But we've tried to bring and open that window slightly to this UNEP report. Have a look in the download. There's also a little booklet I just received yesterday, the booklet for this. It has a bit of an opening door to this metallurgy side, which I think is the lost baby in this whole chain. Recycling is recyclate. No, it's not. It's the final metal. It's the indium high purity. It's the alloy. It's the gold that sometimes goes as gold chloride into the off gas, and you lose it because you've got chlorine in your feed. But you have to know that. And you can deal with it if your system can handle it. So have a look in these reports, which sort of summarize a bit of this topic. So I'd like to end off, Chairperson, with our final sheet of our company, which also has the sustainability report and all that stuff. But the metal side is very much entrenched, and we try to do that as best as we can. And I think we're very good at that. But there are some really daunting exercises ahead of us because we don't have the theory for all of it. So very much like you, we trial it, we do it with clients directly. It doesn't go through the research side, we just do it because there's a need for it. But it's happening. It's not only happening here. If it's not happening here, it's happening in China, but it's happening. So I'll leave you with that thought. Thank you very much.